I'll now start recording. Good. So, what are we discussing today? Today, we're doing a simple and hopefully fairly quick review of multivariable calculus. This will be a very kind of qualitative review in some sense. I will not prove many things. I will just draw some pictures and say that things work. Especially because some of these proofs can either be like long and have a bunch of notation, or they're simple and quick, but I didn't prepare enough to be able to do them without a mistake in 1.5 hours. So, hopefully you get a qualitative picture. With this qualitative picture, you'll be able to compute everything you like. If you then want to sit down and bound things with inequalities, then there's standard textbooks where you can just look this up. Okay. So if we're talking about calculus, one of the things that we want to talk about is a derivative. Okay. But before we define a derivative, let's very quickly define the single most important thing in Math 240 is what is a linear map, right? So let's start with that actually. So definition, and this is not going to be a proper definition because I'm too lazy. So a map T is linear if it satisfies the property that T of u plus lambda v is equal to T of u plus lambda T of v, where u, v are vectors, and lambda is a scalar or a number, whatever you want to call it. So, okay, everyone knows what a linear map is. There's nothing new here. But this is very important. Another person. But this is very important for what reason? For the reason that derivatives are very much linear maps, right? So, in what sense are derivatives linear maps? Well, actually, yeah, sorry. Maybe I should say what we're going to try and do to begin with, right? What's the setup? So the setup is as follows. So before, we kind of have a very good understanding of how to do calculus in one dimension. So in one dimension, we had functions going from where to where. In one dimension, we had functions going from R to R, so from the real line to the real line. We understand how to do calculus on that. Do you agree? So the setup that we have here is I want to generalize that. And now we say I have a function f from Rm to Rn. Okay, so it takes as input m numbers, has as output n numbers. Okay, we have this function, and then we want to generalize a notion of a derivative for something like this. So the main goal, right the next 20 minutes or so, or 30 minutes, is to generalize notion of derivative to f. Okay. Do you agree? Okay. Also, people on Zoom, I'm not reading chat, so if you want to ask something, I will. You have to say it. Okay. So this is what we're trying to do. Okay. Good. So that's right. Let's also introduce some notation. Let's also introduce some notation just so that later down you're not distracted by me introducing notation. Now, when I write f of x, I will mean the following. So x is going to have, how many components does x have? m. Okay, good. So it has x1 up to xm components. Do you agree? And then f of x, this is the output has how many components? N. Okay, so I should have kind of f1 of x, fi of x, going up to fn of x. Okay, so really a function from Rm to Rn, you can think of as n functions from Rm to R. Okay, and then okay, that's another way to think about it. Okay, people agree with this? Yes. Okay, I've not said anything interesting so far. If you let me erase this because this is taking up too much space. Okay, wow, that's very nice. Okay, so now let's finally introduce what a derivative is. So we give the following definition and omit some details as to what a derivative at a point is. So a derivative, is it, okay, sure. A derivative of f at point p in m, not in r m. Okay, the derivative of f at a point in Rm is, okay, colloquially, the best linear approximation to f at p. Okay, this is kind of the qualitative picture that you should have in your mind. What do I mean by this? I mean that if I write f at point p plus some vector v, then I should be able to write this as f of p plus some df, okay, best linear approximation of p. Okay, I'll write it down later. R at p of v. Okay. Sorry. So this derivative we will denote as df sub p. Like this, or maybe what's better? Maybe I put the p here. Is this something people do? I don't know. I will write whatever. Pardon? So a derivative of f at point p is going to be the best linear approximation to f at point p, which I will denote like this: df sub p. Okay. Where, so this is like words. What do I mean by these words? I mean that this object, the f of p, is going to be something that if I take f at the point p and write f at p plus v, right? I look at, you know, some change away from this point p. Then the value of the function will be given, what can be written like this, where f of p is just the value of the function of p. df of p is our, you know, best linear approximation applied to v plus rp of v. Okay, now I need to give conditions on what this is and what this is. So it has to satisfy two things. So first of all, this df at point p is a linear map from Rm to Rn. Okay, and this R, can people see this? Okay, maybe. And this Rp of v is also a map from Rm to Rn, but it is order, meaning what? Meaning that if I was to look at RP of V, take the norm, divide that by the norm of V, and take the limit as the norm of V goes to 0, then this limit goes to 0. Okay. So this is our new notion of what a derivative is. Okay. Let's think about this for a second. Okay. So maybe some people are not so familiar. Okay. So the claim is DFP is the derivative of, so DFP is some linear map. And the claim is that this linear map is the derivative of my function f at point P. If I can write down f P plus V as the value at where I start at, okay, plus this linear map applied to, this V, plus some other P's, okay, where the claim is that this other piece has to be of higher order. Do you agree? Meaning that if I do RP of V divided by V, that should go to 0 as V goes to 0. So in some sense, like if RP had a linear piece to it, right, then that linear piece, the norm of that linear piece should have norm proportional to V somehow. So if RP had a linear piece, then this limit would go to something constant. Okay? If it had some constant piece, then this limit would diverge. Do people see roughly what it is? Like, you can also think of this as like literally a Taylor series. Agree? If I had a Taylor series, all the higher order terms, they're like x squared, x cubed, so on and so forth. And so I'm saying that something is higher order if that divided by x as x goes to 0 is 0. Right? X squared over x as x goes to 0 is 0, so on and so forth. But then x over x as x goes to 0 is some constant. Okay? So in this sense, this is higher order. Okay. And you can believe that, okay, maybe V has multiple components, but we can define what a limit is in a fairly similar fashion to what we had before. Okay? So right, the point is that DFP, right, this linear map only depends on the point P and the function f, right? Then I kind of plug in any V into it to get a best linear approximation to my function. Okay? And so, okay, and so this is some linear map. Okay? Okay, and so you can choose different bases for this linear map, so on and so forth. Different bases to write down the matrix of this linear map, right? And so this is something that we'll do in a little bit. We'll write down what this looks like as a matrix and some bases. Okay, let me see what I want to talk about next. Okay, let's draw a picture and see qualitatively how some of this might be at all true. Okay, let me just move all of this. I actually brought the thing for this, but just placing it like that was fine. I wasn't sure if just placing my phone like this would work. Okay, so let's draw pictures. Is there a second board below this one? No, that's the second board below this one. Okay, and you can ask questions if something is not clear. Okay, so let's draw a picture. We have, I have Rn, do you agree? Sorry, Rm. Okay. And then I have Rn. Okay, and I have some map f that takes a point here, sends it to a point here. Okay. So suppose I have some point P that gets mapped to f by f of p. Okay. So what I want to do is I want to try and do a best linear approximation to how this map takes kind of a little region here. Let me try, please. Takes a little region here and maps it to a region here. It's the best linear approximation, so the approximation will only be good, only be so good. But that's the idea. I want to see approximately how does kind of stuff around here get mapped to stuff around f of p. Okay. So the question, then the next question that we ask, kind of trying to unravel this definition, is suppose I started at p and went kind of v away from p. Do you agree? By some vector v. Do you agree? Then the claim is that this v that I go away from p, once I map through with f, how will this v get? Where will this v get mapped to? Like, where does this get mapped to here? Well, still in the region. Sorry, not where, but like to what specific thing approximately does this get mapped? Yes, df sub p applied to v. Okay. So the point is that if I was to, like, you can think of I have the origin somewhere here, right? P is some vector like this. F of right. Then I'm trying to compute f of p plus v. Do you agree? And the point of what I want to do, I want to split f of p plus v as f of p plus some linear piece in v. Right. So I can say that kind of this v vector, p gets mapped still to f of p, but then f of v, then v gets deformed to some df at p dot v, okay, plus some higher order term. Okay, but we can, plus some higher order term, whatever it is. Okay, but the important part is that up to linear order, right? I get that f of p plus v gets mapped to f of p plus this little linear piece. So in some sense, how I can think of this, I can think of this as kind of my vector v starting at point p gets mapped to some vector starting at point f of p, and this vector is df of p applied to v. Okay, so I should write this down. In some sense, and we will explore precisely what this sense is later, in some sense, I can think of v at p is mapped to df at p applied to v at point f of p. Okay, this is another way to think about it. And well, okay, and then there is still a remainder. I'm just saying, to first order, if we stick to a linear approximation, right? To first order, I can think of it like this. So it's like this plus some higher order terms. Okay. And you can believe me that this is what a derivative was for us in one dimension as well. Do you agree? Because for us, what was a derivative in one dimension? What kind of thing was it? tangent, but when you would be asked compute a derivative, what kind of thing would you be computing? Yes, you'd be computing some number. Why did you have to only compute a number? Because according to this definition, this was what? Yes. What was one-dimensional? So let's do example. So example, suppose I had a function f that goes from R to R. Okay? Do you agree? Yes. Yeah. So then what did I how do I think of this definition? The derivative of f, okay, at some point x is going to be a linear map from where to where? A linear map from where to where? Yes. Yes, from R to R, right? You know, it's going to be a linear map from the input to the output. That's all it is. It's just the best linear approximation. But a linear map from a one-dimensional subspace to the same one-dimensional space, from one-dimensional space to another one-dimensional space. What is that? That is just multiplication by a number. Do you agree? And so what you would say before is let's compute the derivative, and you just compute the number that you needed to multiply by. Okay. But that was the same as computing this. So in this case, this was a multiplication by f prime. Okay, f prime of x. This is what a derivative was before, right? Because you only had one direction, and so this linear map was was just this. Okay. Now df sub x is, I said, in general, some linear map, right? What do we want to have a linear map? Usually, what do I want to kind of try and do for this linear map? Yeah, I want to write down the matrix, get some sense of how it looks like. Okay, for so this is now okay. We've achieved this goal. We've generalized the notion of a derivative for kind of multidimensional functions. Now we want to understand how these derivatives look like. So now goal, I set out a new goal for ourselves. Goal, understand how df at p looks like. And so solution, well, not quite solution, but kind of our approach is write down matrix and basis. And this is actually a very natural thing to do in some sense from the perspective of a first-year student. Do you agree? Because as a first-year student, what do you know about calculus? Well, yes, but what do you know? What do you already know? Example 1. You know example 1. You know how to take a derivative in one dimension. Okay? So what you want to do is you want to reduce what we're doing to taking a derivative of a one-dimensional function. Because that's the only thing you know how to do. Okay? So how are you going to do this? Right? Like, what was the problem? The problem was that here I can go in many different directions and look at the best linear approximation in so many different directions. Do you agree? So if I have many directions, but I only know how to deal with one direction, what do I have to do? Well, sure, but I have many directions. What do I do? Yeah, so I just pick a direction, look at what happens there, and then move on. Right? And hopefully this will make sense. So, okay. That's not gonna help. Yeah, that's not gonna help. I need to watch this again. I watched this like last month. I remember. It's very recent. I know where all the chalk keeps coming on that cloth. I wonder where it's coming from. Okay, so what's the time? Oh, it's very good. Is this even visible? I don't know. Okay. Anything that's visible now. Good. So we don't know how to deal with many directions. So the solution is let's fix some v. Okay, fix some v. Okay. And now, yeah. Now I can just look at my function, how it changes as I go in the direction of v. Okay? So now I can define a new function, which is going to be a function from r to r. Well, okay, I'm introducing a bunch of confusing notation for no reason, but that's a u problem, not a mu problem. I can now define this function from r to r. So fix some direction v. Okay, and then we previously are computing the derivative at some point p. We've already fixed this. P in Rm. Okay, v is also in Rm. So now, so f twirl at v as a function of t is just going to be f of p plus tv. Yeah, that's it. It's just going to be f of p plus tv. You know what? Sorry. Don't write this f of f tilde v nonsense. I don't know why I wrote that. It's not helpful. Not helpful to anyone. Let's just do this. Okay. Not introduce any new notation. Don't introduce any new names for things that don't need to be named. Okay. Now, as you can see, I fixed v, I fixed p. This is a function of just one variable t. This is a function from r to r. We know how to take a derivative of this. Okay. So now, what do we then expect? Like intuitively, we expect this to be the best linear approximation to intuitively, this is a function from r to r. I can now take its derivative with respect to t. Do you agree? And that's something we know how to do. But you can see that what this is kind of doing is it's taking this direction v, right? And just seeing how how all the functions change, how this function changes with respect to me kind of going along this line. Okay? So I would expect that whatever best linear approximation I compute by taking a derivative with respect to t should coincide with what? It should coincide to df p applied to v. So I expect, so this should be true, that if I do df, and then I take this derivative at t equals 0. Okay. You can kind of expect, right, that I know how to do this best linear approximation with t. And then if I do this best linear approximation with t, this is kind of like looking, how do I change if I start walking in the direction of v? Okay. So then I know how to take this derivative, roughly. So then I kind of expect that if I take this derivative, this is going to be some vector. That vector should be precisely df of p applied to v. It should be the best linear approximation in the kind of v direction. This is something that we expect should be true, like just intuitively. At t equals 0, because I want to take the derivative at p. Do you agree? And so to start at P, T is 0 as I start, when I'm at P. And so I want to see if I look a little bit in the direction of V. So then I take the derivative at T equals 0. Okay. Right, because why? In one dimension, this best linear approximation is what? It's f of P plus partial f partial T equals 0 times T degree. Okay, plus some higher order, plus some higher order things T. Right, that's what it was in one dimension, and so I kind of expect this to be very similar. Okay. Okay, so now we have an idea of how to compute, all of these things in principle. Okay, so let's give some notational definitions, and then we'll write down the matrix in this basis, and then we'll say more interesting things. So far, I'm just kind of introducing notation and drawing. Actually, the pictures are useful, and other things not so much. Good. So now, yeah. So now I'm going to kind of introduce another bit of notation, which is just going to be, I'm going to introduce new notation just for this. But that's going to be, this is what people use, and so we should all know it. Let me write this more clearly. Maybe less clear, but whatever. So now I'm going to introduce the following notation. Is kind of differentiating f by some vector v at some point p. What this is going to be, this is just going to be the following. This is going to be, so f is some n component function, right? So this is going to be I'm going to take every single component and look at this component kind of changing in v direction with t, and then take a derivative at t equals 0 for every component. Where this is kind of the usual derivative that you know how to do. So this is t equals 0. Okay, and I take this derivative, p plus dv. Yeah. Okay. So this is what it now means to take a derivative along some direction. Okay. I fully agree. Okay. So remember, f is secretly like n functions, right? Where those functions take m things as input and 1 as output. And so then if I restrict kind of to only look at going in the direction of v, right? Then each one of these functions is now from 1 to takes 1 number as input, 1 number as output, and I can differentiate that with respect to t and take the derivative as required. Okay. Good. So now we've figured out, or at least we've kind of intuited, how we should be able to compute how my linear map acts on any vector. Do you agree? So I gave you a rule that this should be true. Okay, you can this actually, like, you would need to spend a little bit of effort to prove that this is indeed the case. But okay, whatever. It's intuitively clear why this should be equal to this. Okay. So now that we know how to compute how this map acts on kind of any vector, now of course we can write down the matrix for it at some basis. Okay. And this is really silly because this is once again like introducing more notation, kind of like this. And the new notation that we introduced is what? Is partial derivative. Well, this is already a partial derivative. Don't ask me the difference between a partial and a total derivative. It's going to take too long to explain. But now we're going to, right? This is like a derivative with respect to a vector. This is, okay, whatever. What am I saying? No one cares. So we'll now introduce, right, sorry. I'm not explaining this clearly. I wanted to write down the matrix at some basis. Agree? So what basis should I pick that is kind of the most simple thing that, well, not simple, but like, what basis should I pick? Yeah, the usual orthonormal basis. Yeah, so pick kind of this E1 to En basis. Do you agree? So what I want to do is I want to figure out how does df sub p act on E1, E2, and so on and so forth. Okay. M. That's right. Sorry, there's M vectors in Rm. Okay, and I want to figure out how dfp acts on all of these vectors. Ej. Okay. Well, I told you. Okay, it's just going to be, I take this derivative like this. Okay, but instead of writing df partial ej, what people instead write, and so this is kind of, once again, I'm introducing the notation. People write partial f partial xj. Lower or lower? Upper? Okay. Okay, partial xj. Here on this board. Okay. Oh, that's true. Yes. Yeah, I'll just have lower. Otherwise, this is too fine of a detail. Okay. So I will introduce this kind of notation where instead of writing ej, I'll just write xj, because xj is kind of, in some sense, x is the coordinate in the jth component, so that makes sense. And so then, what is this? I can write this now as I take the first function, okay, and differentiate it with respect to xj. Then I take the second function, differentiate it with respect to, okay, at some point p, xg at some point p, okay, and then so on and so forth. Okay. So why is this? Why do people use this notation, right? Because if you were to do this substitution, maybe I introduced too much notation. But, if you were to remember what this was, right? This was just, I had the function f1, okay, and then I took the derivative. So I took the limit as t goes to 0 of p plus t ej minus f1 at p over t. You agree that this is what this stood for? You agree? Yes. But this is really the same as doing kind of f at p, okay, plus 0, 0, 0, xj 0, 0, 0, 0, okay, and minus f at p divided by xj, okay, and I'm doing this at xj equals to 0, and then you can shift it for xj to be the right value. Okay, maybe this is not clear. I'm just talking about notation, but okay. Okay, this makes sense roughly. Yes. So okay. So then in this basis, what does the matrix look like? Yeah.
All we're saying is we pick our standard bases and then you transform it by just transforming every component, and that's what we've done.
So I'm saying that I pick my standard basis, okay, and then I say, okay, if I started at point P and I went along the standard basis vector, how does the function change along that direction? And it will change by this vector.
Yes.
Okay. So this means that the best linear approximation, df p applied to ej, is this vector. Okay. Do you agree? Good. I think I had this problem last time too, and I think last time the layout was also almost the same as to what I wrote. Okay, I will erase this for now. Hopefully people remember what a linear map is. I will keep this bit here though. Good. Okay, so what does the matrix of this thing roughly look like? Right, so if I wrote this as a matrix in this basis, I don't know, right? What do I get? Okay, so this is like if I was to go in the direction of E1, if I was to go in the direction of E2, if I was to go into the direction of EM, right? What do I get out? If I was to go into the direction of E1, so actually, yeah, and this is on the output, I get E1 up to En. In degree, right? I take input in Rm, the output is in Rn. You look confused. What does it make sense?
No, wait. No,
okay, yes. Yeah, you just get those as the columns, that's right. So, I will have things that are like df, dx, right? But I just have to tell you, which f and which x I need to differentiate. By which x I need to differentiate. Well, by which x do I need to differentiate? Is it going to be the one, the row or the column? The x by which I differentiate is the column. The function that I differentiate is the, if it's not the column, it's the row. Okay, good. So let's just write it like this. Partial f. So this is j, this is I, partial fi, partial xj. Okay. Good. So now you know how to compute the derivative of most things. Okay. Okay. This is just, we wrote down a matrix and a basis after 40 minutes of me talking. Very good. Now, what did I say I'm going to do now? Oh, this is not what what I'm going to do now. Actually, no, I already did this, so that's fine. This is not what I had in mind. What are some useful properties that we had for differentiation in one dimension that I want to see how they work in multiple dimensions? No, linearity, like, it's built in. I said, by definition, DFP is a linear map such that all of these things hold. So we know it's, actually, sorry, linearity, yes. Sorry, linearity, you're right. I would want to check it. Yes, okay, but give me more things. It's like too simple. Yeah. Yeah, composition. So I want to check what chain rule looks like. Okay. But actually, now that you mentioned linearity is like a really obvious one to check. And so let's look at that. And let's look at that. And then we'll see how to prove chain rule. Chain rule should be like it should be obvious what it is, and then we'll see why. So one fact that I will state, also without proof, but this is also a fairly easy fact to check, is that if this derivative object exists, right, it doesn't always exist, but if this linear map exists such that these things, then it is unique. Right, so if it exists, it's unique. And you can kind of check, like, oh, if there were two best linear approximations, you could like subtract things and show that it has to be 0 or whatever. Okay. This is just like, fact without proof. You can prove it if you want to. Okay. If it exists, then it's unique. Now, using this, I can prove everything I want. Because what do I have to do? Now, all I have to do is if I have something and I'm able to write it like this, if I'm able to write it in this way and argue that like the kind of additional piece goes to 0 as v goes to 0, and this piece is just f of p, then I know that whatever I have left has to be my derivative. Okay. So now we're going to prove things by pattern matching. I'm gonna write down something and try and make it look like this, and if it looks like this, then I'm done. Okay. Yes. Well, it's not quite proof, but almost proof. Like everything I do is like how you would do it, and then you need to show a bunch of inequalities that things go to 0, and I just don't want to do that. Okay. So let's prove linearity. So I don't know. Theorem and proof. So linearity of what? Linearity of df plus g. If I take the derivative of f plus g at point P, that should be equal to the derivative of f at point P plus the derivative of g at point P. Right? This should be true. So let's prove this. Okay. This is the most boring thing. Right? So what do I want to do? I want to look at my function. In this case, my function is f plus g, right? And look at f plus g at point p plus v, and then write it down in some way. Okay. So I want to look at f plus g at point p plus v. Okay. Well, that's just f at point p plus v plus g at point p plus v. Okay. Okay. I'm sorry. So this assumes if df and dg exist. Okay. So now what can I do here? I know that df and dg exist, so I can write each of these as well. As the expression below, right? I know that the derivative here, so by assumption, the derivative here exists, the derivative here exists, meaning that I can write f of p plus v as something like this. And so what do? I write it as something like this. I write it as f of p plus df at p applied to v plus some rp for f at v, okay, plus whatever, g at p plus dg at p applied to v plus the remainder for g at v. Yes, so this r piece, this higher order piece, it's r because it's the remainder. That's sorry, I should have said this earlier. Okay? Do you agree with this? Okay, well, now I can do my pattern matching. Right, I need colors for pattern matching. Good. So I want to have kind of the constant piece, right? Then I want to find the linear piece, and then I want to find the higher order piece that goes to 0. Do you agree? The constant piece here, and people are waiting, so I'll give them a moment. Okay, yeah, that's fine. So I want to pattern match this expression to be like a constant piece at point P plus some linear piece plus some remainder piece. Okay. What's the constant piece here? Which terms are the constant piece? Yeah. So I will recombine kind of these to be f of p plus g of p. That's my constant piece. What's the remainder piece? Things with r, right? And so you can check that, like it should be clear that if each one of these separately goes to 0 in this limit, like if rp of v divided by v goes to 0 individually as v goes to 0, then if I take their sum divided by v will also go to 0, just by whatever properties of that. Okay, and so this is the linear piece, right? Because you can see this is a linear map in V, this is a linear map in V. The sum of two linear maps is still a linear map. Okay, so then I know by definition, because the derivative has to be unique, I rewrote this thing in some way where I have constant piece, linear piece, higher order piece, that this linear piece has to be the derivative. Right? Because I can do this only in a unique way. And so this shows that this. Okay. So I didn't do anything. I just wrote down the expression. And just from this definition, if we were a little more careful about how this limit works, we'd be done, right? Like there's nothing. Yes.
I didn't quite catch how that P and G. Really like this here.
No, I'm saying this is the constant term.
Ah.
Oh, wait, sorry, I mixed up my colors. Sorry, this is supposed to be yellow. This is supposed to be green. Sorry, I mixed up the colors from this line to this line. Oh, okay. Well, that means I'm very good. I use colors so effectively that even colorblind people can tell the difference. I mean, this is proof. This is not a wild claim. This is okay. People agree with this? Okay. So now let's prove chain rule. Or well, do something with chain rule. Yeah, hopefully this is okay for me to erase. Okay. Chain rule. So what's the setup for chain rule? So I have some function f, degree that goes from where to where? Rm to Rn, okay. And then I have some function g, which has to go from where to where? Not necessarily Rn. What do we want to do? I want to do f composed with g. Do you agree? So g has to map into Rm. So it's Rp. No, yeah, Rk, you're right, Rk. Rk to Rm. Okay. And suppose um, um, that the derivative of g at point p, um, yeah, derivative of g at point p exists, and that the derivative of f at point g of p exists. Okay, do you agree? So let's make this even slower by drawing a picture. Oh, I already have an M here. Let's do George Eliot style. Okay, so I have point P here. I have a map G. This gets mapped to some point G of P. Okay, and this point then gets mapped to some F of G of P. Okay, do you agree? And so let's try and write down the answer without doing anything at all. If I try to write down the answer without doing anything at all, what was what do we want to find? We want to find the best linear approximation of just going from here straight to here. Do you agree? But look, I have a best linear approximation of going from here to here. That's a linear map. Then I have a best linear approximation of going from here to here. That's a linear map. So what should the best linear approximation overall be? Yeah, just I do this linear map first and then do this linear map first. So composition of linear maps. You know, the composition of linear maps is still a linear map. So surely that's the answer. So the answer is that the derivative of f composed with g at point p should be dg at point p composed with df at point g of p, and there should be a little circle for composition here. I'm doing this very poorly. Okay, this is the statement. Now let's almost prove it modulo, showing that all the things go to zero, but all the correct limits go to zero. But that's like a fairly easy technical thing once you think about it or learn the right tools, and it's fairly quick. Yeah, that's right. Okay. How do we prove this? What was our only proof technique? Yes, prove by writing things out and then matching the colors. Okay. Let's do just that. So I have f composed with g, and I want to evaluate it at point p plus v. Oh, this is not going to be enough space, but who cares? Yeah, but then I want this board to be visible, and so you can't move away this board without okay, yeah. So f of g plus gp plus v. Okay. So what's the one thing I know about g? That it can be at point p. It can be written like this. So let's try that. Okay, I'll move this kind of up. So this is going to be f applied to g of p plus dg at p applied to v plus r at point p for function g of v. Okay, do you agree? Okay. Now I want to pattern match further. Actually, I'll give you a chance to write this down. Okay. Now I want to pattern match further. What do I know about f. I know for f that there is a derivative at g of p. So I can now think of this as like, I know stuff for f at g of p plus something. So here I have precisely g of p plus something. Do you agree? Yes.
This current step, can we just reduce R of P, no, R sub P G of P to 0?
No. Why?
Well, because we know it tends to 0.
Well, yes. Yeah. Okay. In principle, you can just realize you can't set it to 0 because at the end of the day, it's something non-zero. It tends to 0 in the limit, but okay, v is not 0, so it's not 0. You can argue that okay, in later computations, it will not contribute to the linear piece because we're trying to compute the linear piece. But right now, well, you could remove it if you knew that in the end it wouldn't matter if it's there or not. But for now, let's do things properly. But that's the right idea. Okay, so now I can realize, this is like my constant piece, and this is like my new direction in which I'm taking a step. So now I can apply this again, okay? But now my kind of v is this whole bit. Do you agree? So I just rewrite this. So I have what? I have f at g of p, okay? Plus df at g of p applied to this mass. Okay, and then plus I'll do RPF applied to this thing again. Yeah, and then now after this, all we have to do is argue which parts are linear, which parts are higher order, and then we're only interested in the linear piece because I'm computing the derivative. There's nothing fancy about this. All I did was I know that, one thing is equal to another thing, and I plug it in. I'm just plugging in things. Okay. Okay. And now I'm essentially done. Right? Because once again, I want to write this as some constant piece for the function f of g at p, right? Plus some linear piece plus some higher order piece, right? What's the constant piece in here? The first f of g of p. Okay. Now here you have to be a bit more careful. Okay. What's the linear piece? Yeah, what's the linear piece? To this. So this is going to be the linear piece. Okay. Now I also have df at g applied to this r for g, and then I have this. Okay. So now all we have to do is argue that kind of this applied to this is going to go to 0 as v goes to 0, and that this applied to this whole thing is going to go to 0 as v goes to 0. Okay. Okay, and so that's the only detail that I'm going to skip. But I mean, you can kind of see it, right? I don't know, composition of limits or something like this.
Okay.
Or actually, no, that doesn't make sense. What I just said.
The R of P,
Yeah.
that's the hard one.
Yeah, that's right. That'd probably be the hardest one. But once again, if you have the right notation, it should be like a 3-line thing. I don't think we quite have the right notation because we have to say what a limit is for more than one variable, which is not that bad, but it's I don't want to talk about it. Okay, and so we realize this is precisely the answer that we wanted, and so that's the answer.
Should the outer remain not be R of G instead of R of P?
This one?
Yeah.
This is, oh yeah, G of P, that's right. That's right. Okay. So we have chain rule. Mm, okay. Good. I think we'll now do two things, and then I'll probably run out of time and stop, unless I decide to say more. What should I erase? Let's erase this. So immediately you get now that you learn chain rule, you get an exercise. And this exercise is very simple. Well, you get a bunch of exercises. But this exercise is, suppose you had a function from R to Rn. Sorry. Let's call this function gamma. And I had a function f from Rn to back to R. Okay. Do you agree? This is some function of one variable. So I should be able to take a derivative of it in one variable. Right? So I go to Rn, and then from Rn I go back to R. So overall, f composed of gamma should be a function of one variable, one output. Show that this is sum over j, and I won't write it like this. It should be partial f partial xj at gamma of t times partial gamma j partial t. Right, I guess I'll still write this sum. Okay, I'll just write this out maybe so. There's no need to write this down. I'm just writing first expression is sufficient. Okay. So prove this, okay? Then this is a j, this is a j, that's right. Is this even correct? Yeah, good enough. Okay. Then I don't know. Another exercise, exercise 2, maybe I should just post them and not write them. Exercise 2 is compute d gamma for gamma takes t and sends it to cosine of t sine of t. Okay. And then do what? And then I don't know, plot d gamma applied to E1 at point gamma of t, and see what you get, and then it should be obvious what you get. Okay. Good. People get the exercise? And now we're going to talk about the last thing, I don't think I'll talk about more. I'll maybe just put it in the suggested exercises. But the last thing is something I talked about in one of the tutorials in the second half of 240. Right? Is we learned about this amazing thing called the determinant. Right? And we learned the determinant tells you what? Yeah, the volume of the parallelepiped, whatever. So surely the determinant of this df thing will be somehow useful. And the question is how? And this is where we go back to drawing pictures. And I've already told you this. Like you've seen this in 240. But perhaps it was a little too quick. Because there I told you kind of roughly the same thing, but in like 10 minutes. So once again, let's draw the picture that I just covered up. Yeah. Right. Sorry. Okay. So I have a point P. It gets mapped to by f into f of P. Degree of f. And so what did we say of how we can think about this df object, right? I can think of this df object as, how to map vectors around the point P into vectors around the point f of P. Sorry, I should be drawing this differently. I should be drawing this as a square and this as like a curved thing. This was point P. Degree. So this is one way to think about it. Is that df is my best linear approximation to my function. So to kind of linear order, in some sense, it's telling me roughly how does a vector here, a vector close to if I was to, how do vectors starting at P and going a little bit away from P, how do those get mapped to vectors starting at f of P and going a little bit away from f of P? Right? That's what's kind of in the formula. I'm taking, if I kind of forget about this term, right? It's almost like I took f of P plus P and turned it into a linear function, right? F of P plus d of P of P. So it's kind of like I'm saying df tells me how does the vector that starts at P and goes to V, how does that get mapped to a vector that starts at f of P and then goes in this direction? Okay? But, okay, so that's what df tells me. But this means what? That in some sense, so if I took like a little square here, I took a little cube I to the m degree, and I wanted to ask you the question. Suppose I take this cube I to the m, so I to the m I mean like some interval to the power of m, like m times. If I did f I to the m, so I took I to the m and I applied it to f, right? I get this new f I to the m. Okay. And this isn't quite. Is this an interval? This isn't quite an interval because it's centered around point P, so it's just some cube around P. But okay, we can figure out what that is. So the question is, this should have volume 1. Do you agree? The question is, what's the volume of this new set? Do you agree? Roughly. So I want to compute the volume of this new set, roughly. But what should the volume of this new set be? Well, no, just give me the answer. I just told you the answer, so you should just tell me the answer. The determinant of df at point P. So it should be roughly this for a sufficiently small cube. Okay. How can we just, like, in terms of this picture, see this? Yeah, I took this cube and I mapped it to here. And I know that to first order, this cube gets turned into this parallelogram by df of P. Right? So I know that roughly f of I to the m is to first order df at P kind of applied to this whole thing. Right? Shifted by f of P. Do you agree? But shifting shouldn't change the volume. Right? So I can ignore it when I compute the volume. And so I'm really looking at the volume of a unit cube being mapped by this linear map. But that's precisely the determinant of this thing. Do you agree? Okay. Okay. And so now we finish with the change of variables theorem by stating the change of variables theorem and understanding why, of course, that's what happens. Not by understanding, but by looking at it and then explaining. Of course, that's what happens. Maybe you don't understand, but that's okay. The picture should be clear. So change of variables is change of variables theorem. Okay. Suppose I have some set V is a subset of Rn. Okay? Rn, yes. So I have, just draw a new, I'm going to erase this and draw a new set inside of it. You guys should just draw a new picture. Suppose I have some set V in here. Okay? And suppose I had some, we're going to relabel like everything. Okay. V in here. And suppose I had some function f coming out of V into the real line. So this was just some function. Okay? And suppose what I wanted to do is I wanted to take an integral of V on V of this function f of x. So this is what I want to compute. I want to compute the integral of this function on this set V. Okay, so I want to do this. So we haven't quite talked about how an integral in multiple dimensions looks like, but you kind of know what it is. The usual picture for one dimension. How do I do an integral in one dimension? An area under the curve, but how do I do that? Yeah, sums of what? Yeah, so I partition my set into, so in your case, you would partition your interval or wherever you're integrating into like little subintervals, right? And then just multiply the area, the length of the interval by like the max or the min or by the whatever of your function of that interval. Here I can kind of do the same thing. I can partition this into like cubes, degree, multiply the volume of each cube. I have a notion of how to compute the volume of each cube, right? That we know how to do. So then I can take this cube, multiply by the volume, by the value of the function on this cube, by some average value or maximum or minimum or whatever, and then add up all of these numbers and get something that approximates my integral, then refine my partition, and hopefully like upper sums, lower sums converge or whatever it is. But conceptually, the idea is the same, right? In terms of this picture. That's true. I cannot partition an arbitrary region. It has to be a nice enough region and there's a bunch of like a lot of details I'm sweeping under the rug. Yes.
Do you worry about that? Like the uniform partition.
So
You don't really care.
you do worry about everything, but not in the span of 1.5 hours. Like we cannot do all of 257 in 1.5 hours, right? I'm telling you this is called review of multivariable calculus. So I'm reminding you of things you already know, right? Exactly. So yes, in principle you're right. In principle I have to be careful. What kind of set is this? You know, what kind of function is this, and so on and so forth. Yeah. Yeah, if it has round boundaries, well then I don't quite get a cube. And so, yes, you're right. But hopefully that is also a detail that we can remember from the past, if we think hard enough. Okay, good. But oftentimes, this is actually precisely the problem. Oftentimes, like I want to compute this integral, but like the region, the boundaries of V are like really weird, right? And so I don't know how to do this integral because I don't know, like, I know how to do stuff if it's like cubes. Like I know how to do cubes, and suppose this isn't quite a cube. So this would be a little bit difficult, okay? And so then you say, aha, hopefully you had, I don't know, some other subset. So this was Rn. Oh, it fell into my pocket, very convenient. So this was Rn. Suppose in Rn, so the same dimension, has to be the same dimension. Suppose I had some, very nice subset. So some subset that I could like much more easily define, what it looks like. And suppose I had a way of mapping this subset into V, so with some function G, okay, such that V was equal to, this is subset U, such that V was equal to G of U, and G was a diffeomorphism. So yeah, what's a diffeomorphism? Diffeomorphism of U and V, meaning that so remember, morphism was something that is what? No, well, before we had like a linear map was a kind of morphism, right? Not necessarily isomorphism, if you had a homomorphism. Homomorphism did what? It preserved the structure of whatever your space is. So diffeomorphism is something that preserves what kind of structure? Like this differentiable structure or something, right? So diffeomorphism in some sense clearly means that G has is somehow differentiable. Okay? And it's a diffeomorphism, so it's probably some kind of isomorphism in some sense, so it should be invertible. So in this case, I think diffeomorphism means that G is differentiable. It's invertible. It maps. It's injective. It maps U into V injectively. The fact that V equals G of U means that it's surjective. So it's some invertible differentiable map, and yes. And I think from that alone, you can, if it's differentiable in one way and is invertible, do I need more things or no? Okay. Okay, that's true. Okay, and the inverse is differentiable as well. The inverse of this map is also differentiable. These are the things we assume. It's differentiable this way. It's differentiable this way. Okay, that's what this is. So now the claim is what? Okay, instead of partitioning this, so now I know that this set is like essentially the same as this set. I just have a way to map this and this. So instead of cutting this up into little cubes, how about I cut this up into little cubes, map those cubes with G, and then use that as my partition. Does that make sense? And I will then use that to try and compute this integral. Do you agree? Instead of computing this integral, let's kind of find a way to relate it to some kind of integral this way. So let's, okay, here I do nice cubes, because hopefully here the region is nice. Okay. And here this gets mapped to some kind of curved cubes. Do you agree? But each of these curved cubes is going to have what volume in terms of this cube? Yeah, it's going to have the volume of this cube times the. Yeah, you should just say the same word you just said. Times the determinant. It's like George Eliot style. You don't have to. You just have to say words. Okay, the volume of this cube. So call this volume. I don't know. Volume 1. Okay. This volume should be volume 1 times the determinant of dg at, okay, some point p1. Okay? Where this point p1 is like some point here. Okay? And then I look at the volume of this cube and take some point here. And then the volume of this cube that's mapped here is going to be the volume of this cube times the determinant at this, other point in that cube. Okay? And so on and so forth. And now I know the volume of this cube now. I multiply that by the value of f here, okay, and then add all of that up. Okay? So what does that sound like? Now this sounds like I look at the volume of this cube and then multiply it by this determinant thing and by this f thing. So that very much sounds like I'm doing an integral over here, but instead of doing it as an integral of the function f, I'm now doing it as the integral of f times the determinant of dg. So this should be f at g, yeah, f composed with g times, so not composition, times the determinant of dg. So let's call this x. Let's call this point x and then dx or something. I don't know. And this is over the subset u. No, dx, dxn, whatever you want to write. No, maybe just not even write it at all. Okay, and this is the change of variables theorem. That's all it's saying. It's saying instead of computing, if I can find different coordinates for this set V, right? This is really in some sense I found different coordinates for the set V. Right? I use these coordinates using G, and G is my coordinate map. Then this integral over this set I can represent as an integral over the set U, where I just have to multiply by how my coordinate transformation changes around the volume of my space. Okay. And so, what exercise should you do? What's something that you can integrate on a circle that's like at all interesting? I don't know. Integrate x squared plus y squared on a circle. I don't know. Yes. Oh, the other side? Oh. Yeah, sorry. Yeah, I forgot about you guys. But it's okay. You remember this from Math 240, so this is fine. Okay. I don't know. Exercise is as follows. So exercise is as follows. You have the set S1, which is the set x squared plus y squared equals to 1. Yeah, sorry. Which is the set of pairs x, y, and R2 such that x squared plus y squared equal to 1. And what I want you to do is I will give you the function f of x is equal to x1 squared plus. Yeah, this is pointless. Yes. Oh, right. They can't. Well, they still can. Actually, no, they can't. You're right. Yeah, they can't. Whatever. I'll come up with an exercise later. I'll post it tonight or something. Right. I want them to compute something on the circle. Okay, we have to wait for your presentation on differential forms before we're able to do that. Okay. Okay. Yes. E to the power of minus square root of. Okay. I'll think about it and then I'll write something out. I want like a very simple exercise where you just have to compute one determinant and it's like a straightforward determinant. Okay. Yeah. I think this is all I have to say for this. Yeah, we don't have time for that. Okay. So this is it. I'll see you all next week.